Good day, ladies and gentlemen. Not a lot of ladies here, but still. I'll try. There is a lot of operating systems around us. I'll try to describe the way that led me to the idea of this operating system, so that it is very unusual. So I hope that you will understand the way I thought to came to this point. The idea was that traditional composite kernel operating systems are more or less outdated, and the world around us tried to move to the microkernel operating systems, and all of the microkernel projects that started at the start of this century, there was a lot of problems with the inter-process communications. If you have the microkernel operating systems, you break down the system into the servers working in a separate address spaces. Then you have to communicate with some kind of IPC between the services. If you break down the system in a real small services, which is an idea basically, then you have a lot of communications. The user program calls one service. This service breaks down the call into the several calls to the second service, and so on and so on. And the overhead for the communications is huge. So the question was, do we really have to break down the code into separate address spaces? What's the idea? The idea is simple. We want to protect code. We want to protect different services one from other. The usual way to protect is based on the Unix paradigm. The separate address space. Can we do it in some other way? Actually, yes. If the language, the basic virtual processor our system works at, forbids you to convert anything to a pointer, then you don't have to protect anything with the different address spaces. You cannot just produce a pointer from, for example, from integer. Then you cannot access any memory. You just have no pointer to. Actually, Java virtual machine and some .NET virtual machine based on the same idea. So the next step was, let's build an operating system around the virtual machine, which protects the memory this way, as I described. And you can get rid of the inter-process communications completely. Your components can communicate by just calling one another with just a pointer to the object. The next question was, well, if we bring such an operating system, build it in a usual way, where start services as a processes. They communicate with pointers, just calling one another. But the next problem is that if the service is not yet started, but you try to communicate with it, the service is just not there. You're calling into the empty space. So the next question was, I think, quite unusual. In every traditional operating system, the process stops when the operating system kernel stops. Do we really have to require the process to stop when the operating system stops? The real answer is no. All the world the process living is operating system, and operating system can hide from the process, from the user space, the fact that the kernel is rebooting. The easiest way to hide it is to build the, well, I'm not in sync with the presentation, but, well, it's, I believe it's okay. I'll get in sync later. If we build the huge virtual address space, which is persistent memory, then the programs living in this huge persistent memory just cannot imagine that there is something wrong around. When the system stops, it seamlessly saves all the state of this memory to the disk. And when it restarts, it rebuilds all the space, and programs just continue to run. Is it easy? The question is, if our system stops abruptly. Somebody just pulls out the plug from the receptacle, and system turns off. Or some hardware malfunctions. We have to build the world which saves the state frequently and doesn't take a lot of resources to do that. Well, I'll try to change to the next slide. Well, why not microkernel? I skip. Think of this memory, persistent memory space having the size of usual disk. So it's not hundreds of megabytes, not 1,000, maybe terabytes. Saving 1 terabyte to the disk is impossible. In one moment, and doing it frequently is impossible. But usually, how usual program works, the big address space is divided to two parts. One is a working set, which is modified frequently in the memory. And second part is usually can be mapped to the disk, but the difference between the memory state and disk state doesn't exist. Like code, when you bring it to the memory, there is no difference between the page in memory and page on the disk. So you don't have to save it. Actually, it is possible to build an operating system which frequently, I mean, once in a minute or even frequently, once in a second, depending on the size and memory requirements of the process, saves all the state of the running processes onto the disk. So this is the idea of the Phantom operating system. To put it really simply, it's a virtual machine, like Java virtual machine, but different, working in a huge persistent memory. Actually, there are new problems which we bring to life when we start to live in such an environment. First of all is garbage collection. Such a system is really a huge application server, different programs working in a big address space communicating. You cannot control memory but by allocating and manually deleting it. You have to work with the garbage collector, and the garbage collector have to collect garbage over the address space of, say, 1 terabyte size of disk. Is it possible? Actually, it is not that it's impossible, but it's very hard. So you can stop the world to collect garbage on this address space, and that was a stopper for me. One moment I thought that it is really impossible to do that, but I found the interesting article saying that it would be really easy to implement a garbage collector if the garbage collector is working not on an actual copy of address space, but on a separate, not changing copy for some moment. So that if we can just take the memory and put a second copy of it, we can collect garbage over this copy of memory, and everything that is garbage in past is garbage in future, so that we can free already. Okay, we can free the memory based on the old state of the memory. For the Phantom operating system, it is usual. Basic idea is to make the copies of address space. So it is possible to write a garbage collector which is working on the snapshot of the memory. such a garbage collector would be quite slow, so that possibly we need second one. And the basic idea at this point is to have two garbage collectors. One of them is working slow and collects all of the garbage looking into the earlier state of the memory. And one of them is fast, but not ideal. It is based on the reference counts, so it cannot collect some kinds of the object structures, such as object loops. But it is okay because the basic task of this collector is to collect fast-going, fast allocated and fast unused objects, such as automatic variables, stack frames like this. Other big problem is the blocking syscalls. In traditional Unix, the application just calls the kernel, for example, asking it to read from the keyboard. In Phantom, it is next to impossible because just the user space is persistent. Kernel is not persistent. Kernel is reboots and restarts from scratch as any other usual kernel. So if your system call came into the kernel code, you cannot restore the state of the user space completely. You just don't know what's going on inside of the kernel. It was a next big blocker for me. I don't have time to describe all the attempts or the ideas to pass through this problem, but the final idea was quite simple. All the blocking system calls are restartable, and they made more or less, no, not more or less, just atomic to the user space. User space calls kernel. The call state is saved. Then kernel does something to execute this call. And if kernel finished, then system call is finished, and for the next snapshot, it is finished. If something went wrong during the system call, like we just turned off the computer abruptly, the system call for the snapshot is just not started. All the state that we need to restart system call is intact, and for the virtual machine thread which restarts on the next restart of the operating system, it just starts in the state when it's just going to start the system call. Well, one of the huge problems for such kind of operating system is that it is very different from everything we have. So thinking about how to bring a user code to this system is one of the main things to think about. For me, I believe one of the best ideas is to build a converter from the Java virtual machine class files to the Phantom class files. I can describe why the Phantom virtual machine is not why I cannot just use, for example, actual Java virtual machine, but I have no time. So I believe that bringing the Java into the Phantom is one of the best ideas, because Java brings a lot of different languages which are possibly compiled to Java. But direct compilation of the languages into the Phantom bytecode is a task too. Up to this year, I was sure that it is impossible to run C programs on such an environment. But now I think that it is really possible to compile C code into the managed environment. There are a lot of problems, but I think it's really possible. One more, thank you. One more idea is that there is a very special processor made in Russia, which is called Elbrus. which contains in the hardware the layer of protection, which is more or less similar to the layer of, to the protection level of the Java virtual machines. It's a processor which forbids you to convert integers to pointers. And on such kind of processors, it is possible to run C code on Phantom operating system and in a persistent environment. But frankly, we didn't even try yet. Not a lot of resources to do that. I'll try to show you this is the overview of the structure of the operating system. The white place on the top is the persistent memory, which is a place for the user code to live in. User code is object-oriented by design, but functional code can run as well. There is a support in the virtual machine for functional paradigm. This is the kernel. This is the lowest level of the kernel, which is made to be portable. So this is hardware independent. This is more or less hardware dependent. It is mostly made for the Intel hardware, but there was an attempt to port it into the ARM environment. Successful attempt, but for now it is not continued. Again, there is not a lot of resources. It's time to for questions, I suppose. So I'm sorry. It's obvious that I need more time, but anyway, I have to stop. And if you have questions, please. Thank you. I don't know.
So this kind of operating system, called single address space operating systems, were built in the 90s. We built one of them for Uni. And the reason why they didn't take off was there was no real actual use case that showed that they had any benefit. And of course nowadays, because you have a single address space, everything needs to be mapped into that single address space. 64-bit address space are not big enough, right? So how do you deal with that?
64-bit address space is more or less okay, but well, you know, actually, when I started to think about this, I just cannot dream about this 64-bit address space. So now it's usual. I believe that's for some 10 years, and we'll have computers with 128-bit address space, which is enough for anything, you know. I hope so. At this moment, I believe that it is okay for the one simple reason. The disk's actual real persistent memory is smaller than address space, and you can map any size of the disk into the 64-bit address space. Maybe, okay, but, oh. We'll wait for even bigger bus. Any questions?
There's been a rise of persistent like RAM in a sense that has become very fast, very cheap, and if you replace like memory that loses data when powering off the machine, so there may actually never be a point where the computer loses its state. Does the operating system concept account for that?
The question is that the newer computers will have non-volatile RAM. Am I right? Yes. Actually, I even have this question in my presentation. It is not true that if the RAM state is saved, then the kernel is automatically persistent. It is not true. You have to, anyway, for Phantom, it's just in you. It just helps it to work simpler, but still you need a kind of kernel which can synchronize the saved state with the changed world. The world is changing anyway. So, for example, just hardware. When you restart, the memory is the same, but hardware is not the same. You still need a layer which synchronizes the state of the operating system to the state of the world.
I didn't doubt
Not yet. Not yet. Yeah.
You've got snapshots of persistent memory. Can you go back in time? And
Yes. No. What is the question? Can we just restart from the one of the earlier states? Yes, of course we can. We can save a lot of the snapshots, and the snapshots are incremental so that they don't lose a lot of disk space. So that then, that's true. That's an automatic backup system. You can return back in time. But you cannot, for example, do a backwards execution. It's not the idea of this system. And one bigger problem, you cannot go back in time for just one application. Only OS system completely. There was a question.
You talked about some special processors made in Russia. Do you have a name for the architecture? Or
Yes, Elbrus. E2K. The short name is E2K. The long name is Elbrus, is mountain.
okay, thank you.
Yes. But it is not dependent on this. So it can work on any kind of the architecture. Any more questions?
How do you handle non-persistent I/O state, for example, network connections and other devices that might be shut down and change their state?
Well, that's a question for another hour of discussion. The question was, how do we handle the situation when the hardware changed its state in some unhandleable ways? For example, if the device is just took down some device from the computer and reset the operating system. To say it simply, some code will get an exception on the next attempt to access this device. Well, I believe it's. I believe it's so. Yes.
So, here if you have more questions.
Thank you very much.